Hello, I am Tim Grote,
And I'm Sam Ragsdale.
and today we are going to be teaching a robot how to do black magic. So the goal of this lab is to teach a robot to cast a simple anti-gravity spell on a pendulum so that it won't fall down when it's inverted.
Before we can begin to teach the robot magic to invert the pendulum, we have to learn how to communicate with it. As a starting point, the robot outputs a range of values from 0 to 4096, which we have to convert to degrees or radians, something that we understand. We also saturate the output voltage to the robot between negative 10 and positive 10 volts, as we don't want to overload the motor or the gearbox.
After learning to talk to the robot, we wanted to be able to control it. Our first task was to get it to rotate between 45 and negative 45 degrees. To do this, we used logic blocks to control the motion, as seen on the right here. As you can see, it's quite a mess. Furthermore, this was a sort of bad solution to the problem. As you can see on the graph below, once it hit the desired positions, it was very jittery.
So next we decided to do a directionally dependent approach. The idea is that it would only switch directions if it were going a certain way and it had passed the threshold. This way it would have constant linear motion in between both of the ends of the range that we wanted.
We attempted to improve on this by adding in a gain that would slow the robot down when it approached the desired positions. And as you can see on the right, the yellow line is the voltage outputted to the motor, and the purple line is the position of the robot. However, this system, while working somewhat well, was very dependent on the exact path we wanted it to travel. So we decided to use a different method of control going forward, as this did not work super well.
So our better solution was to implement a proportional integral derivative controller, or a PID controller. We did this by creating an error signal between the actual position and a desired position. We input this into a PID control, and we sort of arbitrarily picked gains depending on what worked by looking at the two graphs that are shown to the left. The top is showing in yellow the desired position, in purple the error signal, and in blue the actual position. The bottom graph shows how much each component contributes to the output signal.
The gains of each of the three components had a large impact on the characteristics of the response of the robot. For example, the gain on the P portion caused faster overall motion, which gives a better direct response. Increasing the gain on the I block gave a faster response to large errors, but also increased overshoot. But it also was able to reduce the amount of prolonged errors. And finally, the gain on the D block added precision and smoothness and lowered the overshoot, sort of acting to counteract the gain on the I block.
As you can see, this worked fairly well. In the bottom left-hand corner is a scope graph of yellow being the desired position and blue being the actual position.
In order for the robot to be able to fully master the anti-gravity spell, it first had to undergo intense visualization exercises in order to control the magical forces. To do this, we created a virtual robot. On the left, we have our first attempt at defining the envelope of motion for a robot, which we later refined to the version on the right, which is basically just part of the surface of a sphere.
We found the Lagrangian based on kinetic and potential energies, which gives us the top equation for torque in terms of those Lagrangians. We then solve this out to find torque in terms of system parameter variables theta 1 through theta 6. We then used an additional two parameters, theta 5 and theta 6, which represent information about the motor and gearbox.
We then used these equations to find the M, C, F, G, and V matrices, as well as defining a Q matrix that is the position and velocity of each of the two joint variables. We then solved for the derivative of this 1/4 vector using all of the matrices, as you can see in line 23 of the code, to solve for a matrix that gives the velocities and accelerations. We then run this through an integrator and plug it back into a function that does this process in order to simulate the dynamics of the system. Additionally, this matrix is then plugged into a graphing function, which is used to create the simulation as discussed earlier.
The values we initially used for theta 1 through theta 6 were theoretical magical aptitudes. We needed to find the actual for our specific system. So the idea here was to send a specific energy into the robot to stimulate its magical modes. We'd record the output and push it back through a Hamiltonian function to determine each aptitude.
So before we used the Hamiltonian for the real system, we first used it for the simulated system in order to try and retrieve the magical aptitudes that we used in the initial simulation. We did this in order to ensure that our Hamiltonian was correct. After doing that and retrieving the data from the real system, we ran the real data through the same code in order to retrieve the real magical aptitudes for our system. Finding the proper magical aptitude for the real system is important so that the spell does not fail in the end because it misjudges its own capabilities.
Now we were trying to teach the robot to magically control power and control its own power. The first step of this was splitting up the control modes. So we decided there would be 3 different states. There would be a swing up state where the robot was trying to get into a higher state. There's a fall down state where it decided that it couldn't control the spell anymore, so it needed to go back down and swing up again. And state 3 was the ultimate anti-gravity state. That's where the spell was working perfectly, and it was vertical. You can see our diagram, or our control diagram to the right. The other thing we had to do is change the ranges of the input to this control system, whereas where the bottom would have a range of 0 at pointing directly down, and plus or minus pi going up, and at the top it would have a range of 0 pointing straight up and plus or minus pi at the bottom.
In order to implement the swing up protocol, we decided to model Q1 as a function of Q2 and the velocity of Q2. In order to do this, we first modeled the entire robot as a transfer function that we know all of the values for. We then used a desired percent overshoot of 5% and a settling time of 0.15 seconds in order to find the values for zeta and omega n. We then compared these to a known transfer function and a controller with a proportional and derivative gain on Q1 in order to find the values of each of those gains, knowing zeta, omega n, and the characteristic equation. These are gains 5 and gain 7. We then used the error signal of these in order to determine the voltage sent to the motor.
After doing some testing, we decided we needed to add a 4th state where it would, after it fell down, it would come back to the 0 position, the starting position, before swinging up again. This is the control block for that. It was implemented using a basic proportional integral derivative controller.
Having done all this, it was finally time to implement the ultimate anti-gravity spell. To do this, we first linearized the system into the A and B matrices using the Jacobian. And we found the roots of this system to be at 0, -14.8, -5.3, and 7.3, which is unstable because of that positive root not lying in the left half plane. We then used a simple gain matrix, which is just a 4x1 matrix, in order to move all of the roots to the left half plane. We used the place function in MATLAB to move the roots to -5, -5.1, -5.3 plus 2i, and -5.3 minus 2i. And this was able to get the system to stay up and experience anti-gravity.
These are three graphs of voltage during the ultimate anti-gravity spell. The left shows a swing up and catch where it becomes stable. The middle shows a destabilized ultimate anti-gravity spell where it ultimately saturates beyond its power of -10 volts. And the right shows a stable system.
So we can see here the final system that we used after a few more modifications, where the voltage is outputted after the multi-port switch on the right-hand side. We can see at the very top the case switch function, which controls which mode the robot is in. Connected to the first port of the multi-port is the swing up function, as discussed earlier. The modification to this is at the bottom left we now have the ability to have a desired position of Q1 inputted in, which is going to basically every other state. And as you can see in state 3, we have just the same gain matrices as discussed earlier.
So here's a demonstration of the swing up of the robot to ultimate anti-gravity. As you can see, it can smoothly and reliably swing up and balance from start as well as from being knocked down.
So here we have the robot already being in the ultimate anti-gravity state, and what you just saw there was it moving to a new position that we set. As you can see, it is able to move to a desired position without falling down.
This is a time signal input for our desired Q1. As you can see, it can smoothly move in between Q1 positions without falling out of the ultimate anti-gravity state.
So in this one we have the anti-gravity state following an analog input from a ball. As you can see at the bottom right, as Sam moves the ball, the robot rotates around, and it is relatively resilient to falling down.
This is a demonstration of us entering a new Q1 desired position that's too far outside of its range, so it falls outside of its range and it's still able to get up. It shows that it's more resilient to big changes.
So here we have the robot in the simulated space. Right now it is doing the swing up protocol, and as you'll see here, we also have the ability to obviously move it to a position, but it falls down because we made too large of a change. So for this project, while each step was important, steps 5 to 10 were most important. Steps 1 through 4 were really more about learning to interact with the robot and preparing for the later steps, but steps 5 through 10 were where we actually started to control it.
In the end, the robot was able to do each mode in both the real and simulated. This is except for simulated ball and beam control. That's due to just modes in Simulink, as we were running in normal mode for the simulation and the analog input required the external.
Additionally, for each step there were a couple of different implementations that we could have used. So this was not the only method that would work. However, other implementations would still rely on the same sorts of ideas to solve the problem.
And overall, it was very successful.